This is Lecture 5 for Chapter 5, Calculus 3, and it is on the vocabulary for paths and surfaces and some of the integrals along paths. Okay, so what is a path? When we think of a path, we often think of a trajectory of an object, but in vector calculus, most curves are called paths whether or not there is an object associated with them. They're called plane curves, though, again using the word curve. They're plane if they're in a two-dimensional plane, such as the XY plane. Otherwise, they're space curves, and I think we already know that from the earlier chapters of this class. And of course, we're going to want to parameterize both the plane and the space curves. Here are some properties of the paths. A path is considered simple if it doesn't cross back and loop back on itself. It's closed, obviously, if the endpoints are the same. And now it's oriented if a unique normal can be assigned to every point. It's oriented positively, or has positive orientation, if the curve can be traversed, as though you pretend you're walking around this curve, or walking around this path, in a counterclockwise manner. And in this case, you want all those normals to point away from the enclosed region. So you're walking along a closed path, and you want all the normals to point out. Of course, the obvious example is a circle, and you want to say, well, let's get another color. You want to start here, and you want to walk along here in a counterclockwise direction, and you want the normal to the surface. Right here, you could, the plane curve, it's pretty obvious. On the space curve, it's a little different. You want these normals to be pointing away from the enclosed region. And as you point away, then your right hand, if you have a good handle on which one's your right and which one's your left. Okay, so not everybody does, especially in sciences. At any rate, so you're standing here, supposedly your right hand, like I say, if you know which one that is, will be pointing away from the enclosed region, and your left hand would be over here. That's called positive orientation to a curve. These are just obvious examples of simple and closed curves. Sometimes, for example, in the piecewise example, the region has a hole in it, and you might wonder why it would still be called oriented positively, and that you would still be traversing it properly if some of it looks like it's traversed in the clockwise direction. For example, this, with the arrow going here, is obviously in the counterclockwise direction, but this inner C2, this curve along the inner portion here, look what direction that's going. If you can see it, it's going clockwise. It doesn't violate this principle because the normals would still be assigned pointing away from the enclosed region. See, and the way it's actually done is that as you come along here, and then you take this cut, so that when you go in with this cut, you can go around this loop and come back out, and then you can finish your path. All right, or you can go over here. Notice that integrating along here and integrating along here would cancel each other out because just the endpoints would be different. These are various cuts that you can make when you go and do integrals along these paths. And now we have this similar vocabulary for a surface. It's closed if it completely encloses a three-dimensional region. Obviously these don't. And it's oriented if unique normals can be assigned to each point on the surface. And note that in this case you might have you have actually two normals, one up and one down here. You obviously could have another normal as well. The one on this side, right over here, actually is supposed to be representing a bulging surface, like part of a soccer ball cut off from the rest of the ball, not an enclosed blob. Now once you get a closed surface, which obviously this thing looks like it's closed, it's positively oriented if the normals that you are using point away from the surface. This is positive orientation. Negative orientation would mean that the normals are pointing inward toward the enclosed surface. This is just vocabulary, like I said, it's to keep signs and communication straight. If you always use positive orientation, you get a certain sign for that integral. Someone could do the same integral using the the normal's pointing in another direction, and they would get a different sign. Well, what's wrong? The integral isn't wrong, it's just that they used a different orientation. So in order to keep all this communication straight between people and results, we have this vocabulary for these closed surfaces and curves. Now when you start talking about a region, say an enclosed region, then you like to talk about its boundary. It's typical to use this symbolism for boundary. So if R, that's right here, R is the region, and you use what looks like a del, you know, like for partial operator, and del R means the boundary of it, or sometimes just by itself, right, like I said here, and that denotes the boundary of it. Now notice that if the region, the boundary, the dimensions of the boundary are always one less than the region. For example, if you have a solid object, that would be, it would be a dimension 3, then the boundary is two-dimensional because it's a surface, right? If you have a region in the xy plane of dimension 2, then the boundary is just a line that goes around it of dimension 1. You can get this idea here, right, in this diagram. This is a two-dimensional region in the xy plane, and the boundary are, well, different sections of one-dimensional lines and curves that go around it. If this is a curved surface in three-dimensional space, and it's really a surface, that's what the sigma denotes here, then the region around it is a line. Well, this slide should have been a little bit before I showed you how to make the cuts in it, but when you have these regions, they're connected. Obviously, if this was your region, it's not connected. What connected means is that any 2 points can be connected by a path that lies entirely in the region. Okay, it doesn't have to be a straight path. Simply connected, that means you can take this, a closed curve of the region, and if you put a closed curve around the external, as a boundary of the region, you can shrink it down to a point. And something, this is simply connected, this is simply connected. You could just shrink this thing down to where it's just a point in here. Same here. Obviously this is not simply connected. And this isn't either. But again, it's one of those cases that you could handle this one by making cuts if you needed to integrate around it. The purpose of this lecture is just to give you in one spot the definition of simple, connected, and oriented and positively oriented, just to put them together in one spot, not to study the details and the intricacies of these kind of regions. That's the course, you need to take a course in topology for that. Now if you make an integration over the region or over the boundary, some of these have special names and physical significance. If you're talking about a scalar field, you can integrate it, of course, along a path, over a surface, over a region, and it has the names or the significance of being mass, first, second, moments, and other quantities if the scalar field is density. Okay. We have other results if we're talking about a vector field. Okay, now the other that I said so far was interesting. This is very, very important though. So pay a lot of attention to this. When we integrate a vector field, remember we're dealing with vectors, we break that field into two components. One component is perpendicular, tangential to the surface, and that, I'm going to call that V parallel. Then we have another vector or component of the vector that's perpendicular. Obviously if we're over here, then the tangential component would look like that, and the perpendicular component would look something like this. Okay, so this is going to change at every path where this vector is coming through. Say this is a vector field and all of them point in that direction. That's what I was assuming. But the vectors could point different directions on the surface, but at each point on the surface you can, especially if you use a different color so somebody can see what you're doing, you can resolve that into a perpendicular component and a parallel component. Okay, and then integration of the perpendicular component and the parallel component have different results, different names. Okay, if you integrate the normal component, that's the perpendicular component, that is, and you integrate it over a surface of a region in space, that is what's called flux. It's as though you're looking at the amount of vector field that comes through that surface. Integration of the tangential components is called circulation. Sometimes it's called flow also, but you're meaning flow around something, so it's kind of confusing because the vector field could be flow itself. But if you're integrating that tangential component, if it's a force, that can be the work. Of course, you can integrate that over a closed or open path. But let's look again at what we're talking about here. Okay, I'm back to this slide. Now, when we integrate the normal component, so I'm just going to draw a bunch of more vectors on here. I'll draw them in blue like the one that you see there. Okay, say this other normal component is, here it is here, here's the normal component here. These are all going to be, I'll call V perp, which is normal, and then coming out of this point might be this normal, V perp. Okay, you see what we're getting is the amount, if this is the vector field, the amount that's parallel, that's tangential, is sort of like flowing around on this surface. This is the amount that be flowing through it, and if you integrate, that means add up all this V perps, you get the flux. That's the flux that is coming through this surface. When you integrate the tangential components, okay, there you get the circulation. What I'm going to mention here is sort of a highlight for the later chapters of the book, and that would be of the class, and those are the theorems of vector calculus. They're very important, and they're way at the end, and maybe we don't spend enough time on them. But if you take a surface and say it's totally enclosed, and you have a vector field going through it, give it a different color. Say this vector field is doing something like this as it goes through, and you integrate all the perpendicular components, okay, and you're integrating these perpendicular components on the surface. There is also another integral, and that's the integral of the field over the inside. And so the integration of a vector field over the closed boundary and the integration of certain derivatives on the inside, there's a correspondence between them. And that's what you get with these theorems of vector calculus, because sometimes it's easier to take the integral of this derivative over the region than it is to try to integrate the perpendicular or the parallel component over the surface. And that's a little look ahead at the last part of this chapter 5 on theorems of vector calculus.